So again, folks, we're getting towards the end of the first marking period here. We said what we were going to get to at the end of the week here would close off the marking period. We're going to finish up 3.3 today, and I want to talk about 3.4 as well. So that quiz might go into Monday or Tuesday of next week. So we want to cover 3.3, 3.4, have a quiz on 3.3 and 3.4, and we'll use that quiz to then close off marking period 1. So a completion homework out of 3.3, a completion homework out of 3.4, and then we'll take a quiz on 3.3 and 3.4. So those last 3 grades we'll cover the end of the marking period, and we'll get grades out to you as soon as we possibly can. Back into 3.3 then, we talked about the power rule for positive and negative integers, stating that the derivative of x to any positive or negative integer power n would be equal to n times x to the n minus 1. We bring the exponent out as a multiplier and then subtract 1 off of that exponent to get our power rule. We looked at the multiples, the sums and differences, and then we looked at the product and the quotients as well. So just a quick review then. Let's glance over at that cheat sheet that we had. We had number 1, the limit definition. We had the limit as h approaches 0 of f of x plus h over or minus f of x all over h. And then we had the limit definition to find the derivative at a clear-cut point x equals a, giving us the limit as x approaches a of f of x minus f of a over x minus a. That will find the derivative at a particular point. Okay. We then went into the power rule, the product rule. What was the product rule again? If we wanted to take the derivative of some function u times a function v, what was the derivative of u times v equal to? V times u prime plus u times v prime. Does order of addition make any difference? Absolutely not. So could we have uv prime plus vu prime? Yes. I write it the other way around, though. I write it as vu prime plus uv prime because then it's very similar to the setup that we have for the quotient rule as well. What's our quotient rule? If we're going to take a function u and divide it by a function v, what is the quotient rule equal to? vu prime minus uv prime all over v squared. Okay, so again, u represents your numerator, whatever your numerator function is, and v represents your denominator, whatever your denominator function is. With the product, it really doesn't make a difference. Okay, so from there then, let's take any questions if we have any out of the 3.3 assignment that we're hopefully working on. Any questions out of the 3.3 that you've come across yet? Number 5. Directions, they just want us to find the derivative. In number 5, find dy dx. Again, that's notation for the derivative. So in number 5, we've got basically powers of x. And if it helps you in number 5, let's rewrite this as y equals x to the third divided by 3 would be the same as multiplying x cubed by what coefficient? Yeah, 1/3. 1/3 of x cubed plus how many times of x squared? 1/2. 1/2 of x squared plus 1x. So dy dx, using our constant and our sum and difference rule, would be equal to 1/3 times the derivative of x cubed plus 1/2 times the derivative of x squared plus the derivative, plus the derivative of x. So running through now our power rule, we would get 1/3 times, what is the derivative of x cubed using our power rule? 3 times x to the 3 minus 1, good, plus 1 half times, what would the derivative of x squared be? Yep, 2x to the 2 minus 1. Derivative of x, again, that's x to the first, that would just be 1x to the 1 minus 1. And then simplifying this all down, dy dx, or y prime, whatever you choose. They said dy dx here, so let's use that. What is 1/3 of 3? 1x to the second, plus what's 1/2 of 2? 1x to the first, plus anything to the 0 power is, times 1 is 1. So we get a derivative x squared plus x plus 1. That would represent what three things? Slope of the curve at any point, x equals a. Slope of the tangent line to the curve at any point, x equals a. And the third thing, our instantaneous rate of change, which is what 3.4 is really going to get talking about, is the velocities and the rates of change, using the derivative to represent those. Okay. All right with 5? Okay. Any other questions we've got off of 3.3 thus far? Which one? Number 9? Find the horizontal tangents of the curve on number 9. We need horizontal tangents. What is the slope of a horizontal line? 0. So we need to find where we're going to have a slope equal to 0, and then plug that in. Okay. So we know to write the equation of a horizontal line that our slope is going to be 0. Okay, so ultimately we're going to write an equation. Y equals m times what? X minus x1 plus y1. We know that our slope is going to have to be equal to 0. So we know that this equation of the line is just going to be y equals y1, a horizontal line. We just need to find out, though, where our slope is going to be equal to 0. At what value of x, or values of x, will that slope be 0, so we can find the corresponding y value? Well, how are we going to find out the slope so that we can set it equal to 0? We're going to find the derivative, yep. So dy dx is going to be equal to the derivative of x to the 4th minus 4 times the derivative of x squared plus the derivative of the constant 1. Okay, make sure you're very consistent and very concise with your notation. Okay, you'd hate to lose simple points for notation. Derivative of x to the 4th. Using our power rule, what would the derivative of x to the 4th be? Yep, 4 times of x to the 4 minus 1. Minus 4 times, what would the derivative of x squared be? 2x to the 2 minus 1. The derivative of any constant is, and make sure you write that 0 initially to show that you know that the derivative of a constant is 0. Now, simplifying this down, dy dx, 4x to the 3rd minus 8x. Minus 8x. So that represents our slope anywhere on the curve. What are we going to set that slope equal to now then? Yeah, we're going to set that slope equal to 0. What can we factor out of that binomial? 4x, leaving us with x squared minus 2. X squared minus 2 equal to 0. So we're going to get values of 0 at x equals 0 and at x equals positive and negative radical 2. Positive and negative radical 2 when we solve those down. For x equals 0, so therefore x equals 0. X squared minus 2 equals 0, so x squared equals 2. And now we got to take the square root of 2, but there's two of them. There's positive and negative. So our tangents will be horizontal, or our slope will be equal to 0 at these three x values. So what we need to do now is find their corresponding y values. Where are we going to go back to find the corresponding y values when x equals these three values? Back to the original function. So at x equals 0, scoot back up here a little bit, we're going to get y equal to what? Yeah, 1. When x equals 0, that'll knock out, we're left with 1. Y equals 1. At x equals positive root 2, what's radical 2 to the 4th power? 4. What's radical 2 squared? 2 times 4 is 8. So 4 minus 8 would be negative 4, plus 1 would be negative 3. We'd get a y value of negative 3. At x equals negative root 2. What's negative root 2 to the 4th going to be? Same thing, right? What's x squared going to be when it's negative root 2? The same thing. Are we going to get the same y value? Yeah, we're going to get the same y value again. Y equals negative 3. So summarize this up now then. At x equals 0, positive and negative root 2, there will be horizontal tangents and then stay with those horizontal tangents are going to be horizontal tangents of y equals 1 and y equals negative 3. Always make sure you summarize up what you've done. Don't assume that the grader knows what you're doing. Okay? The grader needs to assume that you know nothing. You've got to show your full understanding of the problem. Okay? So we found our derivative because we know the derivative represents the slope of the curve. We then took our derivative to set equal to 0 because we wanted a horizontal tangent. A horizontal tangent has a slope of 0. So we found out where the horizontal tangents will occur at. And then we came over here and found the corresponding y values. Now we know a horizontal line, again, is just going to be a y equals y1 equation. So that's why we found these y values. So y equals 1 and y equals negative 3 will be our horizontal tangents at those corresponding spots. All right with number 9? Good one. Mm-hmm. Yes. Yep, absolutely. So what Trent is asking is instead of doing this right here, instead of using the sum and difference rule to split all those up, could we just do d dx of x to the 4th minus 4x squared plus 1? Absolutely you can. Okay. But this right here, can you skip this? No. Do not skip this. This right here shows your understanding of the power rule and the multiple times a function of x. You can't skip this. You really do need to show this here because that's showing your understanding of those basic derivatives. Okay? Yep, absolutely you could do that. Other questions we've got from the start of the homework? 31. Directions again to find just dy dx. Find the derivative in 31. There's going to be a couple things we're going to do here to 31 to make it a little bit easier on us. One of our major rules so far has been the power rule. So I'd really like to re-express these as powers of x. What is the square root of x equal to as a power of x? X to the 1/2. This is x to the 1/2 minus 1 divided by x to the 1/2 plus 1. And now there's really a couple roots we could take here. We've got a quotient, We've got one function of x divided by another function of x, so we could use what? We could use our quotient rule. Could we rationalize this? Absolutely, and if we rationalize this, we might get just a simple power of x. Ultimately, is it going to make a difference? No. Technically, does our power rule work yet for fractional exponents, though? No. At this point right now, our power rule only works for positive and negative integers. So technically, we don't know that the power rule is going to work for a rational power of x. Okay. Ultimately, yes, it does, but at this point right now, we haven't shown that it does. So what I'm going to do is I'm going to rationalize. What do I want to multiply the numerator and the denominator by if I wanted to rationalize the denominator? A radical x minus 1. What's that term called? The conjugate. Radical x minus 1. So when we FOIL out the top, what's radical x times radical x? X minus how many radical x? Yeah, minus 2 radical x from the inner and the outer. And then the last is going to give us plus 1. All divided by, again, radical x times radical x will be x. What's going to happen to the inner and the outer? They're going to cancel. A negative radical x and a positive radical x will cancel and end with a minus 1. Okay. So we get x minus 2 radical x plus 1 over x minus 1. So ultimately that really didn't help us out a lot because we still have that radical. We still have a function of x in the numerator and a function of x in the denominator. So ultimately here we're still going to have to use what rule? Yeah, we're still going to have to use the quotient rule. It's not going to make a difference. So actually, this right here will be a little easier to use the quotient rule on than that right there. This only has 2 terms top and bottom. This one's going to have 3 terms in the top and 1 or 2 in the bottom. Okay. So I'm going to use my quotient rule with this right here. Okay, I went through this process just in hopes that we might be able to simplify this down, but we really weren't able to. Okay. So I'm going to define u to be equal to my numerator, x to the 1/2 minus 1. And I'm going to define v to be the denominator, x to the 1/2 plus 1. Tell me, folks, will these two functions have the same derivative? Yes. Why will they have the same derivative? They're not the same function. Why will they have the same derivative? Yeah, the only thing they differ by is that positive and negative 1. They differ by a constant. But what's the derivative of a constant? 0. These two functions will have the same derivative. Okay? So u prime is going to be equal to 1/2 x to the 1/2 minus 1 minus 0, which ultimately will be 1/2 x to the negative 1/2. Same thing over here. V prime will be the exact same thing. 1/2 x to the negative 1/2. Okay. So let's define then what dy dx is going to be equal to. Since it's a quotient, what is our quotient rule? Make sure you always state this. The quotient rule is vu prime minus uv prime all over v squared. And we've got everything well defined up here. Okay. So as we substitute in dy dx, our v is radical x plus 1. Our u prime is, bless you, let me keep these as x to the 1/2, I guess. X to the 1/2 minus 1. Our u prime is 1/2 x to the negative 1/2. Our u is x to the 1/2. Wait, I'm sorry, this one's a plus 1, right? Yep, that's a plus 1. U to the 1/2 minus 1. Our v prime is 1 half x to the negative 1 half. And our v squared is x to the 1 half plus 1 squared. And now it's just a process of simplifying this down, combining like terms. dy dx. We've got to distribute up here, so we're going to get 1 half. And what do we do with our exponents when we're multiplying like basis? We subtract them. What's 1 half minus a negative? Minus a negative becomes, I'm sorry, we add, right? Add, I'm sorry. Same division. We add. 1 half plus a negative 1 half would be a 0, right? So 1 half x to the 0 plus 1 times anything is itself. So 1 half x to the negative 1 half. And now from this, we've got to subtract this quantity over here. Again, what's x to the 1 half times 1 half x to the negative 1 half? X to the 0 minus 1 half x to the negative 1 half. Down here, I'm just going to leave this x to the 1 half plus 1 squared. I'm not going to FOIL it out at all. Okay. Anything to the 0 power is 1, so this is really 1 half, but over here we're subtracting 1 half, so 1 half minus 1 half, what's going to happen to those? They're going to knock each other out. Minus a negative becomes plus a positive. So 1 half plus 1 half is 1. So we get dy dx to be x to the negative 1 half over x to the 1 half plus 1 squared. Now the last thing that I'm going to do here now, did they start off with rational exponents or did they start off with roots? They started off with roots. I'm going to turn this back into roots. Okay. A negative exponent is going to take this really to where? The denominator. X to the 1 half is root x, but that root x is going to go to the denominator because it's a negative exponent. Parentheses, root x plus 1 squared. And this is all over what now then? 1. 1 over root x times root x plus 1 squared. What should we do with this one definitely? I'm going to graph it out. I'm going to graph this out and verify that our derivative is correct. Okay. So into the calculator. We are going to type into y1. And actually, I'm not even going to graph it out. I'm just going to verify y values. Y1, we want math 8. We want the numeric derivative of a parenthesis root x, close the root, minus 1. Close your numerator, divided by, open your denominator, root x, close the root, plus 1. Close the denominator. Okay. So root x minus 1 divided by root x plus 1. We want to take this derivative with respect to x, and we want to take the derivative at all x. Close it out. So we're taking the numeric derivative of root x minus 1 over root x plus 1 with respect to x at all x. y2. For y2, we will be typing in the derivative that we came up with, which is 1 divided by the quantity. Root x, close the root x, parentheses, root x, close again the x, plus 1, close the quantity, squared, close the whole denominator then. Okay, and then I'm just going to go second graph, which is our table. I got a data type error somewhere along the line. I think I've got to close another parenthesis right there. 1, 2, that closes that one, that closes that one, that closes that one, that one closes that one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I don't know why that's a data type error. Hmm. Numeric derivative, we've got open the numerator, open the x. It, this closes the root. This closes the numerator. This closes the denominator, that closes that. Let me see what that, this still says data type error. We need that parenthesis there. Numeric derivative, this opens our numerator, square root of x minus 1, closes the numerator, divided by, this opens our denominator, that closes our denominator. So we're taking the square root of that function with respect to x for all x. I don't know why that's coming up with a data type error. Are you guys getting that error, or is yours going? I've got 1, 2, 3, 4, 5 opens, and we've got 1, 2, 3, 4, 5 closes. 5 opens, 5 closes. It keeps taking me back to when it gives me the error, and it keeps taking me right to here. Your guys aren't doing that though? Are they matching up? Y1 and Y2 values the exact same? Okay, so we knew our derivative is correct then with doing it. I'm not going to waste any more time here then. I don't know why that data type error is coming up, but if your guys are working. Okay, so are we correct on that one then? Yes. Anything else from the homework that we've started so far? Okay, let's go ahead and get back into the notes then. It's not going to take us very long to finish these up. Again, we've looked at examples of pretty much all of these that we've done so far going into those couple questions that we've looked at. No sense in reviewing them again. I believe we were at the point of looking at this example. Is this correct? Okay, we haven't done the example yet, but we were at the point. Okay, so they want us to find the equation for the line tangent to the curve at y equals 1 over x at the point 1, 1. Okay, so again, we've got to write an equation. Y equals m x minus x1 plus y1 is the equation of a line. We need to know two things. We need to know a point and a slope. Did they tell us the point? Yeah, x1 is 1, y1 is also 1. Now, did they need to tell us the point? Could they have just said x equals 1? Yeah, and if they just said x equals 1, we would have thrown it in here, and we would have found that y equaled 1 as well. But how are we going to find the slope? Yeah, the slope is going to be equal to dy dx, which is d dx of 1 over x. Okay, now we could look at 1 over x as being a quotient where our u is 1 and our v is x, but it would be much easier for us to re-express this as y equals x to the negative 1. Y equals x to the negative 1 would be a lot easier. Okay? So the derivative of x to the negative 1. Okay? So our slope is equal to our derivative, dy dx. So using our power rule, what's the derivative of x to the negative 1? Negative 1 times x to the negative 1 minus 1. So our slope is equal to the derivative of y with respect to x, which is negative 1 x to the negative second. Or if you want, negative 1 over x squared. Negative 1 over x squared represents our slope. Or negative 1x to the negative second. It doesn't make a difference. Okay. Now, we're specifically concerned with x being what? 1. So, at x equals 1, our slope is equal to negative 1 over 1 squared, which is still what? Negative 1. Still negative 1. So now coming back up here then, we get y equals, our slope is negative 1, x minus 1, plus 1. We don't have to simplify that down, but it's easy enough to do it. Negative x, negative 1 times negative 1 would be a positive 1, plus 1 more would be plus 2. Y equals negative x plus 2 would be the equation of the tangent line to the reciprocal function, y equals 1 over x at the point 1, 1. Okay, and I'll save us the time by going in and graphing it. We've got the graph of it right here. So here's the reciprocal function, 1 over x, the hyperbola. And then here's the line y equals negative x plus 2 coming across. So right here's the point 1, 1. That is the point of tangency. Point of tangency. Can I also write the equation of the normal line, folks? How do we write the equation of the normal line? The negative reciprocal slope. Yep. So then the normal line would have a slope of positive 1. Yep. The normal would have a slope of positive 1. Questions on that example at all? Okay, let's get into higher order derivatives. Taking second derivatives, third derivatives, so on and so forth. Okay. Right now we're doing just the first derivative, but we can keep taking derivatives of functions. We can find its second derivative. We can find its third derivative. And as we get into chapter 4, we're going to really explain the uses of the higher order derivatives. Okay. In chapter 3, we're just going to be basically computing them, running through and finding second and third derivatives, or any higher ordered one. But then we'll really get into the applications of them into chapter 4. So the derivative, y prime dy dx, is called the first derivative of y with respect to x. But that first derivative may also still be a differentiable function, which we could take the derivative of then the first derivative, and so on and so forth. Okay? So if so, we get what we call the second derivative, y double prime. And then these here then are all the different notations we've got for a second derivative. Okay. Y double prime, or dy prime dx. So now we're taking the derivative of the first derivative. Or d dx of dy dx. Dy dx represents the derivative, so we're taking the derivative of the derivative to get the second derivative. Or this is the big one over here. The front one and the end one are the big ones. d2y, the second derivative of y with respect to x. d2y over dx squared. Okay. This one here, the prime notation, and this notation are the big ones. Okay. They represent the second derivative. Okay. And we can move on and so forth. We could keep taking the derivative of the second derivative and get the third derivative. Or the third derivative of y with respect to x. We stop the prime notation with 3. We're not going to continue to write prime after prime after prime. As we go on farther, we get to what we call super n. We'll go y super n, which represents then the fourth derivative, the fifth derivative. So for an example, this right here we call y super 4. We're taking the fourth derivative, or if there was a y6, we'd be taking the sixth derivative, so on and so so forth. So again, we're only going to do prime up to 3. So y prime represents the derivative, y double prime is the second derivative, y triple prime is the third derivative, but we're not going to go any farther with the primes. We'll go super n. Okay, I believe they've got that on the next slide. Yep. Okay, so the multiple prime notation begins to lose its usefulness after 3 primes, so we use y parentheses n, which is read y super n. So d dx y n minus 1, all those represent the same thing then. So that's the nth derivative. Okay. That's it. Yep. And that's just what I was going to go into right there. Yep. Without parentheses, you're taking a power of your function. With the parentheses, it's a derivative. So y parentheses n represents that higher order derivative versus just y to the n would be a power. So the parentheses is a higher order derivative. Without parentheses, it's just a basic power. Okay? Yep, so be very clear with your notation there. Do they have an example of us taking a higher order derivative? No, they do not. That was the last section of the notes there, right then? Okay. Let's go into our homework and see if we can find a higher order derivative in the homework. 33? Okay, we'll take a look at 33. Yep, find the first 4 derivatives of the function in 33. So they want to find the first, second, third, and fourth derivative of number 33. And it's kind of nice because it's a straightforward polynomial function. We're going to be able to take the derivative of a polynomial until you get down to a constant to be at 0. So let's use the prime notation. So y prime would be equal to d dx of x to the 4th plus x to the 3rd minus 2x squared plus x minus 5. So y prime would be equal to, what's the derivative of x to the 4th? 4x to the 3rd. Plus, what's the derivative of x cubed? 3x squared. Minus, what's going to be the derivative of 2x squared? Minus 4x. Plus, what's going to be the derivative of x? 1. What's the derivative of a constant? 0. So there's our first derivative. Y prime is 4x cubed plus 3x squared minus 4x plus 1. The second derivative now then, y double prime is going to be the derivative of 4x cubed plus 3x squared minus 4x plus 1. So our second derivative, y double prime. What's going to be the derivative of 4x to the 3rd? 12x squared plus the derivative of 3x squared? 6x minus the derivative of 4x? It's just 4. The derivative of 1 is 0. Okay. Y triple prime, our third derivative, is going to be the derivative of our second derivative, 12x squared plus 6x minus 4. So our third derivative, y triple prime, what's the derivative of 12x squared? 24x. Plus, what's the derivative of 6x? 6. Derivative of 4 is going to be 4x up here. So 1 times 4 is 4, but then 1 minus 1 would be x to the 0. 0. 0, yep. So then down here, what's the derivative of this? 0 as well. Okay, and now then, we're not going to use that prime notation anymore. We use super n. So y super 4 represents the fourth derivative. Y super 4 would be the derivative of our third derivative, 24x plus 6. So y super 4 would be equal to what? What's the derivative of 24x? Yeah, just simply 24. The derivative of the 6 is going to be 0. Okay, so this is kind of a nice straightforward polynomial example. Let's generalize this then. What's the degree of the polynomial we started off with? It's a fourth degree. What's the derivative of a fourth degree polynomial? A third degree polynomial. What's the derivative of a third degree polynomial? A second degree polynomial. What's the derivative of a second degree polynomial? A first degree polynomial. What's the derivative of a first degree polynomial? A constant. And then what would the fifth derivative be? The fifth derivative would be 0. You can take polynomial functions and lead them to a derivative of 0. It just depends on how many times. Now we had a fourth degree, and our fourth derivative was the constant, so a fifth derivative would get us to the 0. So one derivative more than your degree will lead you to 0 on any polynomial function. So if we take 3 derivatives of a quadratic, we would get 0. Okay. All polynomials are somehow derived from that y equals 0. Yeah. Yeah, the concept of zooming in and making it locally linear. Making it locally linear. Okay, as we keep zooming in. Okay. Questions on that example at all with 33? Okay, so that finishes up the section. The homework will be due for tomorrow. And again, it's on page 124. We're going 1 through 33, the odds. So we've looked at, 5, 9, 31, and 33. Were those the ones we did? 5, 9, 31, and 33 are taken care of. We got 38, 40, 46, and 47 as well. So 38, you're finding tangents to the curve where the slope is 4. So instead of having your slope be equal to 0, you've got to find your derivative and set it equal to 4. 40, the x and y intercepts of the line that is tangent to the curve at that point. So finding x and y intercepts. 46 and 47. Cylinder pressure question in 46 and a free fall question in 47. Now 46, they're saying if gas in a cylinder is maintained at a constant temperature, so T is a constant, the pressure is related to the volume V by the formula this right here. So you may be familiar with this from physics or something like that, I'm not sure. But key here, A, B, N, R, and T are all constants. A, B, N, and R are constant values. So basically, P is a function of V. So P is your Y value, V is your X value. Everything else is constant there. So P is just a derivative or a differentiable function of V. Okay, and then they want you to find the derivative dP dV. Down here in 47, they want you to find the first and the second derivatives of that free fall equation. The first and second derivatives. Okay. Any other questions again here on the homework that you've started? Okay, we'll use that as an endpoint then for today. So again, 124 will be due tomorrow. Tomorrow we'll get into 3.4 and hopefully cover 3.4. This is a shorter section. And hopefully look to the quiz Monday, Tuesday at the very latest. And then we'll close off the argument. Okay, sounds good.